Imagine just for a moment that everything you see, every star in the night sky, every planet in our solar system, all originated from a singular, unimaginably small point. Hi everyone, today we're diving into one of the most mind-blowing concepts in cosmology, the Big Bang, the theory that explains the origin of our universe. Let's start at the very beginning, about 13.8 billion years ago. Picture this. All the matter that makes up our vast universe was compressed into a tiny point known as a singularity. This isn't just small, it's small, infinitely dense and unbelievably hot. In this singularity, the fundamental forces of nature, gravity, electromagnetism and the nuclear forces were all unified. Then, in less than a blink of an eye, something extraordinary happened. This singularity expanded. It didn't just grow, it exploded in size at a rate that's hard to fathom, doubling every fraction of a second. This event, known as cosmic inflation, created space itself. It's like unfolding a gigantic cosmic origami, revealing the universe as we know it. As this newborn universe expanded, it began to cool. Particles formed, collided, and merged, creating the building blocks of everything. Quarks came together to form protons and neutrons, which then assembled into atomic nuclei. Electrons began to whirl around these nuclei, crafting the first atoms. Light, which had been trapped within this dense soup, finally began to travel freely. From these humble beginnings, the cosmos continued to evolve. Galaxies, stars, and planets emerged, sculpted by the invisible hand of gravity. Stars burned brightly, forging heavier elements within their fiery cores. And when they exploded as supernovae, these elements were scattered across the cosmos, seeding future generations of stars and planets. And as a testament to this incredible beginning, we have the cosmic microwave background. This faint glow, permeating the entire cosmos, is the afterglow of the universe's infancy, providing us with a snapshot of those first moments. So when you look up at the night sky, remember you're not just looking at stars, you're looking at the echoes of the Big Bang, the moment everything began. In the vast expanse of the cosmos, there's a hidden player that shapes the universe in ways we can barely fathom. This unseen force is known as dark matter, and it holds the key to many of the universe's mysteries. But what exactly is dark matter? Dark matter is a mysterious and elusive form of matter that plays a crucial role in shaping the cosmos. Here's what we know. Dark matter doesn't interact with light or the electromagnetic field, which makes it invisible. However, its presence is inferred from gravitational effects. These effects cannot be explained by general relativity unless there's more matter than what we can directly observe. Imagine a galaxy as a cosmic dance of stars, dust, and gas. Dark matter acts as the invisible glue that holds everything together. It constitutes the majority of a galaxy's mass and forms the foundational structure of our universe. In the standard cosmological model known as lambda CDM, the universe's mass-energy content consists of ordinary matter. This includes the familiar protons, neutrons, and electrons, the stuff we see and interact with daily. It accounts for only about 5% of the total mass. Dark matter makes up approximately 26.8% of the universe's mass. It doesn't directly interact with ordinary matter or radiation except through gravity, dark energy. The remaining 68.2% is attributed to dark energy, an enigmatic force responsible for the universe's accelerated expansion. Detecting dark matter in the laboratory is challenging because it doesn't emit, absorb, or reflect light. Its primary interaction is gravitational. Scientists have been searching for an as-yet undiscovered subatomic particle, possibly weakly interacting massive particles, WIMPs, or axions, to explain dark matter. Dark matter is classified based on its velocity. Recent models favor a cold dark matter scenario, where structures gradually accumulate from particles. However, gravitational wave observations and the James Webb Space Telescope suggest that primordial black holes could also contribute to dark matter. While most astrophysicists accept dark matter's existence, a minority propose modifications to the laws of general relativity. These include theories like modified Newtonian dynamics or entropic gravity. However, none of these alternatives can fully explain all observational evidence. As we continue to explore the cosmos, the quest to understand dark matter remains one of the most exciting and challenging frontiers in science. As we journey through the cosmos, one of the most intriguing phenomena we encounter is gravitational lensing. But what exactly is it, and how does it work? Gravitational lensing occurs when massive foreground objects, such as galaxies or black holes, bend and warp the fabric of space itself. Let me explain further. Imagine a distant light source, such as a quasar, a young active galaxy, emitting light. This light travels through the vastness of space, heading toward us. However, between this distant light source and us exists a massive celestial body, often a galaxy cluster or a black hole. This massive object creates a strong gravitational field in space due to its immense mass. According to Einstein's theory of general relativity, massive objects curve the fabric of space-time around them. As the light from the distant quasar approaches this curved region, it encounters a warped space. This warped space-time acts like a lens, bending the path of light. The more massive the foreground object, the stronger the lensing effect. The light rays from the quasar get deflected, creating a distorted but magnified image of the quasar. In some cases, the lensing effect produces a circular or elliptical pattern of light around the massive object. This phenomenon is known as an Einstein ring. The background light source appears as a ring or partial ring due to the gravitational bending. Gravitational lensing can also create multiple images of the same distant object. These images appear at different positions around the foreground lens, each corresponding to a different path the light took around the massive object. Gravitational lensing is more than just a cosmic curiosity. It serves as a powerful tool for astronomers, allowing them to study distant galaxies and dark matter. By analyzing the distorted images, scientists can infer the mass and distribution of unseen matter, including dark matter, that bends the light. As we continue to explore the wonders of the universe, gravitational lensing stands as a testament to the beauty and complexity of the cosmos. It reveals the hidden forces at play and helps us understand the intricate dance of light and gravity shaping our universe. The Bullet Cluster is a remarkable cosmic collision, a massive collection of two large groups of galaxies located approximately 3.8 billion light-years away from Earth. Let's explore its intriguing features. Collision event. The Bullet Cluster formed after a violent collision between two large clusters of galaxies. These clusters were hurtling toward each other at tremendous speeds. The collision itself ranks among the most energetic events since the birth of the universe during the Big Bang. Observable evidence for dark matter. The aftermath of this colossal collision provided dramatic evidence for the existence of dark matter. Dark matter, although invisible, exerts gravitational influence on its surroundings. Its presence can be inferred indirectly through its effects on visible matter and light, components of the Bullet Cluster stars. The stars within the galaxies were not significantly affected by the collision. Most of them passed through the chaos, gravitationally slowed but otherwise unchanged. Hot gas, intracluster medium. The hot gas in the two colliding components, observable in X-rays, represents most of the baryonic ordinary matter in the cluster pair. These gases interact electromagnetically and slow down more than the stars. Dark matter. The third component, dark matter, was detected indirectly through gravitational lensing of background objects. Unlike ordinary matter, dark matter doesn't emit or absorb light. Its gravitational pull bends the paths of light rays, creating lensing effects. Gravitational lensing and dark matter. In theories without dark matter, such as modified Newtonian dynamics or MOND, gravitational lensing would be expected to follow the distribution of baryonic matter, that is, the X-ray gas. However, in the Bullet Cluster, the strongest lensing occurs in two separated regions near the visible galaxies. This supports the idea that most of the cluster's gravitation arises from two regions of dark matter, which bypassed the gas regions during the collision. Dark matter's behavior aligns with predictions. It interacts primarily through gravity and weakly interacts otherwise. Cosmological implications. The Bullet Cluster's extreme temperature makes it one of the hottest known clusters of galaxies. It serves as an observable constraint for cosmological models, especially at temperatures beyond their predicted critical cluster temperature.